So I wanted to do a vector addition problem where we're mainly working with magnitude and angles of the vectors and being able to break those down into x and y components in order to add them together properly. Because when we talk about vectors and we add them together, they have to be in the same direction or along the same line in order to be added. Now I want to make note of the fact that in this particular problem, the directions north, south, east, and west are taking the place of x and y directions, but we really can think of them as x and y directions anyway. So north-south is y direction, east-west is x direction. So the problem is that we have this sailboat. The sailboat is in winds that are changing, and so it has sort of a path that's crooked. So what it does is it starts off and it just goes 2 kilometers straight in the east direction. Then the winds shift and it travels 3.5 kilometers in the southeast direction. Now, when we're talking about directions, southeast direction or northeast or northwest or southwest, whenever you see a direction indicated like that, it means it's directly in between the two directions. So southeast means it's at a 45-degree angle measured from the east or measured from the south. Same thing with those other directions. Always implies a 45-degree angle if we use that. If it's something different from a 45-degree angle, it would be noted like this. It might say it goes in a direction 30 degrees north of east or 50 degrees south of west. And so that's going to tell us how we measure it relative to the different axes. So you have to be careful. Now, the third leg of the journey, the sailboat travels in a direction that right now we don't know. We're going to call that vector C. But what we do know is when it gets to the end of that leg, the net displacement of the sailboat is it's 5.8 kilometers in the east direction. So the way that I've labeled these 3 legs of the journey are with vectors A, B, and C, and I'm saying that they add up to give me vector R, which is the final displacement from the beginning. So A plus B plus C equals R. We're going to use this and our knowledge of how we add vectors using components to figure out the x and y components of vector C, and then we'll be able to figure out vector C, its magnitude, the magnitude of that leg, and also what direction it points in. So for leg A, which is the first one, the x component is just 2. It's 2 kilometers. The y component is 0. It just went straight east. It didn't go north or south, and so the y component is 0. For B, bx is going to be b times the cosine of 45 degrees, where b is 3.5. And so this gives us a component of 2.47 kilometers. This is kilometers too. By. Now by is negative. I'm going to put in that sign because taking the sine of 45 degrees would not give me a negative sign. I would have to, actually I would have to measure the angle all the way around in order to, and use that big obtuse angle in order to get the negative sign automatically. But because I know it's pointing down, I can put in that negative sign. I know that it's negative. This will be minus 2.47 kilometers. And I know that the sine and the cosine of 45 degrees is identical, but I'm still going to use sine and cosine to emphasize the fact that for one, I'm looking for the side that is opposite the angle, therefore I want to use the sine. And for the other component, I want to use this, I'm looking for the side that's adjacent to the angle, and that's why I would use cosine. So because of the fact that these 3 vectors added together are well, Cx and Cy, I should just say we don't know, we're going to look for it. But because these 3 vectors added together gives us 5.8 in the x direction, I'm going to use the fact that I can add all the x components together to find the x component of the resultant and all the y components together to find the y component of the resultant. So for instance, Rx is equal to Ax plus Bx plus Cx. And this is going to end up giving us an algebraic expression that will be very easy to figure out what Cx is. Rx is 5.8, Ax was 2, Bx was 2.47, and Cx we don't know. Cx is going to be 5.8 minus 4.47. And so that ends up to be 1.33 kilometers. So we found the x component of vector c. Now we're going to do the same thing in the y direction. What did I do? Y direction. Listen to what you're saying. So Ry is equal to Ay plus By plus Cy. Again, it's going to give us an algebraic expression. Ry is 0, Ay was 0, By was minus 2.47, and Cy we didn't know. That one's pretty easy. Cy is 2.47. Now I know the x and y components of vector c. I can now use the Pythagorean theorem to find the magnitude of c by taking those two components, squaring them, and taking the square root of them. And I get a magnitude of 2.8 kilometers. So vector c has a length of 2.8 kilometers. The angle that it's going to be directed at, which is this angle right here, I would find by taking the inverse tangent of cy over cx. Remember, because I would say that the tangent of that angle would be the y component over the x component, and so then I would rearrange it to figure out what that angle is. Put in the numbers there, writing kind of small, but what our angle ends up to be is 61 degrees. So now I have actually found the complete expression for vector c. I need to specify how big it is. It's 2.8 kilometers long, and it points at an angle of 61 degrees. In fact, if I wanted to describe that using directions, I would say that it was 61 degrees north of east. And so I like this problem because we're adding vectors together, but it was a little bit of a shift because we had to find one of the vectors that we're adding instead of just summing them all up. But the technique is always the same. So hopefully this is a helpful example.